Hello friends, welcome to my third lecture on languages and grammars. In this lecture we shall discuss the various types of the grammar. The grammars are classified according to the types of productions which are permitted. Type 1 grammar. Let us see what is type 1 grammar. A grammar is said to be of type 1 if every production alpha goes to beta has the property that norm of alpha is less than or equal to norm of beta. Now, let us remember that the norm of this notation I am calling it norm alpha. Norm alpha means the length of the string alpha. Okay. So, this is length of alpha is less than or equal to length of beta. Now, norm type 2 grammar, if every production is of the form a goes to beta, that is the left side is a variable, a is a variable as we know, okay, and the right side beta, beta is a word. It consists of one or more symbols. So, here the left side is a variable, okay, the right side is a word consisting of one or more symbols. Now, in the type 3 grammar all the productions are of the type a goes to a or a goes to ab. A you know small a is it is a terminal symbol. Okay. So, either a goes to a, okay, left side you can see left side is a variable, right side we have a terminal symbol. So, a goes to a or a goes to a terminal symbol a followed by a variable. Okay. So, we can see the left side is a single variable, okay, the left side is a single variable a here also a. So, left side is a single variable, right side is either a single terminal like here it is a single terminal or a terminal followed by a variable. So, here we have a terminal a followed by a variable b. Now, we can see each of these types of grammars, okay, they allow the trivial production s goes to lambda. How? You can see norm of s or sorry length of s is 1 because it is one symbol, length of s is 1, length of lambda is 1. So, it satisfies the inequality length of alpha less than or equal to length of beta. Further, it is also there in type 2 grammar because it is of the form a goes to beta. A here is replaced by s here and in place of beta we have lambda. Okay. Now, it also belongs to the type 3 grammar because it is of the type a goes to a, okay, s goes to lambda. So, this s goes to lambda is there in all the 3 types of grammar. Okay. A type 0 grammar has no restrictions, okay, on its production. So, if we do not if we have a case where type 1 grammar, type 2 grammar, type 3 grammar none of the 3 apply, then that case will be the case of type 0 grammar. There is no restriction on this kind of a grammar. So, let us see a language types of language. A language L is called to be of type 1, 2 or 3 according as it can be generated by a grammar of type 1, 2 or 3 respectively. Now, let us look at this example. Determine the type of the grammar G which consists of the productions S goes to A goes to AAB, B goes to B, A goes to A. Now, here you can see left side is a variable, here is single variable S here, A here, B here, A here. Okay. Right side is a word, okay, which consists of one or more symbols. Here we have a terminal A and a symbol A. Here we have a terminal A, there are 2 symbols the 2 variables A and B. Here we have a terminal B and a terminal A here. So, left side is a single variable, okay, in the case 1 left side is a single variable while the right side is a word made up of consisting of one or more symbols made up of there are 2 symbols here A and A, there are 3 symbols here, small a, capital A, B, there is one symbol here, there is one symbol here. So, the first case, in the first case the grammar generated by these production rules will be of type 2. Okay. So, type 2 grammar. Now, let us go to the second case, S goes to A B. Okay. A B. Now, here you can see, here there is one variable on the left side, here there are 2 variables on the left side. Okay. Here there is one variable on the left side, here there is one variable on the left side. So, this grammar, the grammar generated by these production rules cannot be of type 2. Okay. It cannot be of type 3 also. Why? Because in the case of type 3 we have S goes to A, or we had A goes to A goes to A, or A goes to A B, that is a terminal followed by a variable. Okay. So, either A should go to a, either we should be having a terminal, okay, or we should have a terminal followed by a symbol. Now, but left hand side should be having a single variable. Here there are 2 variables here A B. So, it cannot be of type 3 also, but it can be of type 1. In the case of type 1 we have alpha goes to beta and length of alpha is less than or equal to length of beta. So, here length of S is 1, length of this A B is 3, okay. Length of this is 2, length of this is 2, okay. Length of this is 1, length of this is 1, length of A is 1, length of A B is 2. So, each of these production rules satisfy the inequality length of alpha less than or equal to length of beta. Okay. So, in the case 2 we have type 1 grammar. Okay. So, because each of the production rules satisfy the inequality length of alpha less than or equal to length of beta. Now, let us go to the second example. Determine the type of the grammar G which consists of the productions S goes to A B goes to C, A goes to B goes to B. Let us look at this first, whether let us see whether it is of type 1. Okay. Type, in the case of type 1 grammar we have alpha tends to beta, it consists of productions of the type alpha tends to goes to beta, where length of alpha is less than or equal to length of beta. Type 1 grammar is generated by such kind of productions rules. Okay. So, here you can see we have this A B tends to goes to C. So, length of A B is equal to 2, length of C equal to 1. Okay. So, A B goes to C does not follow this rule. Okay. Length of alpha less than or equal to length of beta. So, this is not, this first case is not of type 1 grammar. Is it of type 2 grammar? In type 2 grammar, okay, we have rules of the type, production rules of the type S goes to alpha. Okay. S goes to alpha, where no, A goes to alpha, where A is a variable, A goes to alpha. A, so, left side is a single variable. Okay. In the type 2 grammar, left side is a single variable, right side is a word, okay, which consists of one or more symbols. So, here left side should have only a single variable, while here we see left side has 2 variables. So, it is not of type 2. Okay. Now, it is not of type 3 also. Why? Because type 3 grammar is generated by production rules of the type A goes to A or A goes to A B. Okay. So, left side here again is a single variable, here left side is a consisting of 2 variables. Okay. So, it is not of type 3. Okay. When the grammar is not generated by type 1, type 2, type 3, we call it as type 0. Okay. So, the first case is of type 0 grammar, because it does not follow any rules. Okay. Type 0 grammar. Now, let us go to 2. So, S goes to A B. Okay. So, here there is a single variable, here there is a single variable, here, here, here and here. So, all are single variables. Now, let us see, here we have a terminal followed by a variable, here we have a terminal followed by a variable, here we have a terminal, here we have a terminal, here we have a terminal followed by a variable, and here we have a terminal. So, all these production rules are of the type variable goes to a terminal or variable goes to a terminal followed by a variable. Okay. So, the second case is of type 3 grammar. Now, let us discuss context sensitive grammar. A grammar G is called context sensitive if productions are of the form alpha A alpha dash goes to alpha beta alpha dash, where beta represents any non-empty string. Empty string, as we know, is denoted by lambda. So, this grammar is called by the name context sensitive because A can be replaced with beta only when A lies between alpha and alpha dash. Now, a grammar G is called there is another type of grammar which is called as context free if the productions are of the form A goes to beta. This grammar is known by the name context free because we can replace A by beta regardless of where A appears. Now, let us note that context free grammar is the same as type 2 grammar. In the type 2 grammar, if you do not consider the production of the form A goes to lambda, we are not, if you do not consider in type 2 grammar, then the grammar type 2 grammar is same as context free grammar, because in the context free grammar this beta is a non-empty string. Okay. So, we cannot include A goes to lambda. So, from the type 2 grammar, if we do not consider the production of the form A goes to lambda, then it is same as context free grammar. So, here in the context free grammar, A is replaced with beta regardless of where A actually appears. In the type 2 grammar, if you recall what we had said, type 2 grammar consists of productions of the type A goes to alpha, where on the left side we have a single variable, on the right side alpha is a word consisting of one or more symbols, and type 2 grammar includes A goes to lambda. So, if you remove A goes to lambda from this type 2 grammar, then it is same as context free grammar. Now, derivation trees. Let G be a context free grammar with the following productions: S goes to AAB, A goes to BBA, B goes to BB, B goes to C. Then the word W equal to AC, BA, BC can be derived from S as follows. You can see we want to derive W equal to AC, BA, BC. Okay. This word we want to derive. So, what we should do? First of all, we should start with S. S goes to AAB. Okay. Now, we want AC, BA, BC. Okay. So, A goes to BBA. Okay. So, we write A goes to BBA and we have B here. Okay. Now, if you use the production rule B goes to C, then we will have AC, BAC, we will not reach here. Okay. So, we should not use B goes to C here. Okay. What we should use, because we want AC, okay, yeah, for this we can use this B goes to C. So, this goes to, for this B we use B goes to C. So, we have AC, BA and B. Okay. And for this B, now if you use B goes to C, then we will not reach here. So, for this B we use BB. So, AC, BA, BB. Okay. So, we have AC, BA. Okay. Now, we want BC. So, we can go to now AC, BA, BC. Okay. So, S goes to A, B used first, then we use the second production rule, A goes to BBA to reach this. So, this is first production rule, let me say this is first, then this is 2, this is 3, this is 4. So, let us see in what sequence we are using. Okay. First we are using production rule 1, okay. Then we are using production rule 2 and then we are using production rule 4, okay, to come to this place, and then B goes to BB. production rule 3 we are using here, okay, and then we are using 4. So, 1 2 4 3 4 if we use like this. So, S goes to A B, then we have A B A B, and then we have A C B A B B, okay. This B I can I have not written this step here. So, A C B A B, this is implicit here, A C B A B, and then B is replaced with B B here, and then we ultimately replace B with C. So, we reach here. So, you can see this when you allow context free grammar, then B goes to C, wherever B occurs can be replaced with C. Okay. Now, derivation trees, we will come to that. Before let me also say, let G be the context free grammar with productions S goes to A S, A B S. Find the derivation tree of the word W equal to A B A B A. First, let me write the sequence of sequence in which we shall use the production rules. So, S goes to, now S goes to here, S goes to A and S goes to A S, okay, because we have this notation means S goes to A, S goes to A S, and we also have A goes to B S, okay. Now, let us see in what sequence we shall use these production rules to reach the word W equal to A B A A B A A, okay. So, S goes to, first we shall use this, S goes to A S, okay, S goes to A S. Now, A goes to B S, we have to use that because we want A B, okay. So, A goes to B S, okay, and we have S here, okay. Now, what we do, if you write S goes to A, so we shall have A B A, okay, A B A, and this S we should then use replace by A A S. So, this now goes to A B, this S can be replaced with A here, okay, and then we have S, S now goes to A S. So, A B A S, okay. So, we have A B A we have. Now, what we will have A S, A goes to B S because we want now B A. So, we want this to A B A and A goes to B S, okay. So, this now goes to A B A and B S goes to A. We want, yeah, S goes to A. So, we will have B A, okay, by using this production rule, S goes to A. So, S goes to A will then bring us lead us to A B A B A. So, by using the production rules in this sequence, we arrive to the word W equal to A B A B A. Now, this sequence can be represented by a derivation tree. Let us define what we mean by derivation tree. Before that, thus we have a, if we have a context free grammar and a string that is derivable from the grammar, then to exhibit the structure of the derivation, it is useful to draw a derivation tree or parse tree, okay, because it allows us to interpret the string correctly. So, let us see what is a derivation tree. A derivation tree is an ordered tree in which each vertex is labeled with the left side of the productions and in which the children of a vertex represent its corresponding right sides. At the root of the tree is the non-terminal symbol with which we begin the derivation, okay. The leaves of the tree represent the terminal symbols that arise. For the production A goes to W, where W is a word, the vertex representing A has children vertices that represent each symbol in W in order from left to right. For the production A goes to lambda, lambda is the empty string, the vertex representing A has the single child lambda which has no siblings. The yield of the tree is then the string of symbols obtained by reading the leaves from left to right, omitting any lambdas encountered. Now, let us see how we get the tree here. In this case, say for example, derivation tree if you want to write, we will have S here, okay. let us say this is my S, S goes to A, B. Okay. This is the first production rule. Now, then we replace A with B B A. Okay. So, A with B B A. Okay. B B A. Okay. B B A. Then second one is what we did, A replaced with B B A. Now, what we did was B we replaced with C. Okay. So, B with C. Okay. And then B A B. Okay. So, A C B A B. Okay. And then what we did in the next step, A C B A B B replaced with B B. Okay. So, B replaced with this B. Okay. This B we replaced with B B. Okay. B we replaced with B B, and then B we replaced with C. Okay. Now, you can see this is these are vertices, this is vertex, this is vertex. Okay. This is vertex. Okay. This is vertex and this is vertex, they are vertices, and these are children's. Okay. So, A C B A B C. So, we read them from left to right. You can see from we start from here. So, A C B A B C. Okay. And we get this A C B A B C. Okay. So, this is the children, this is the derivation tree in this case. So, among these production rules, which sequence of production rules when we apply in this manner will lead us to the word A C B A B C. So, this how we reach the word A C B A B C can be exhibited by means of this derivation tree. Now, let us look at in this case what we will have. So, S, this is my S, start symbol S, then S goes to A and S. Okay. And then we use A goes to B S. So, B S. Okay. A goes to B S, and then we write S goes to A. Okay. So, S goes to A, B S, this S goes to A. Okay. And this S now goes to A S, A S. Okay. The right S, rightmost S. Okay. This S goes to A S. Okay. And then A goes to this A goes to B S. Okay. And then the two S, okay, this S and this S both go to A. Okay. So, now we can read the from left to right, A B A B A, and we have A B, okay, A B A B A B A. So, this is the derivation tree in this case. So, the derivation tree or we also call it as a sparse tree, derivation tree or parse tree. Okay. It allows us to interpret the string correctly. We have to simply read it from left to right, as we have seen here. The yield of the tree is the string of symbols obtained by reading the leaves from left to right. If there is any lambda in between, B lambda we omit. Okay. Omitting any lambda is encountered, that is not read when we read the leaves from left to right. So, this is how we draw a derivation tree. With this, I would like to end my lecture. Thank you very much for your attention.